Finishing up with our chapter 11. Well, continuing with chapter 11, we're going to do one more type of t-test, and this is for a two-sample difference of means. So our goal is to be able to test hypotheses that are drawn from two-sample data and dealing with means. So here's an example. I want to talk about what might fit with this situation, where it says, has the mean number of hours Americans work a week changed? One of the questions on the General Society survey asked respondents how many hours they work each week. Responses from a random sample of employed Americans were recorded from 1975, or for 1975 and 2014. They're summarized here to compare the 2 years and how things have changed in that 40-ish year period. These data give convincing evidence at an alpha level of 0.05 significance of a difference in the true mean number of hours worked per week for Americans from 1975 to 2014. Okay, you think like the typical work week is 40 hours. So that data is there. How can we do this? How can we compare them? It's going to be so similar. This is going to be quick because it's going to be so similar to a two-sample confidence interval, but we're using a test. So we want to still start off with the same sort of ideas. We want to have two parameters. We're going to use mu sub 75. That's going to be the true mean hours worked per week for Americans in 1975. And then likewise, we're going to do it for 2014. Okay? Continuing on, we need to have some hypotheses based off of this situation, right? We need to make a hypothesis and test a hypothesis. So my hypotheses for these will be, I'm going to say, we're just trying to see if there's a difference, right? So mu sub 75 equals mu sub 14, whereas our alternative would be that they're not equal. So now that we have that set up, we can check some conditions and we can go into our actual test. Now the conditions, again, are going to be the same as it was for a two-sample t interval, where, number one, we want independent random samples from the population, or if we have an experiment. This is just, really, it's data from an observational study. So we're going to say, does it say random? Random samples. All right, so we have independent random samples of technically employed Americans in both years, so 1975 and 2014. Yes, that was stated. All right, now for our approximately normal distribution of hours, that's what we're looking for. Oops, approximately normal distribution of hours worked. This would be for both. We have to check both. Now, we have enough of a sample size for both because it was 764 and 1501. They are both covered by the central limit theorem. Greater than 30, 1501, greater than 30. Both, yes, by the central limit theorem. All right? Now we do have to check one more thing because it is sampling. It's not an experiment. So we have to check the 10% condition for both. Would we say that 764 is less than 10% of all 1975 Americans or employed Americans? Yes. And 1501, same thing from 2014. Again, yes to both. So our conditions are covered. It means we can go on with our test and feel good about it because we have met the conditions to use the things we need to use in this test. Now this is going to be a 2-sample t-test for what? For a difference of means. Okay, not a t-interval, but all the same sort of deals. Now, how are we going to do find our t-value? Here's where I want to pause and go to our gold sheet and kind of fill some things in here. Because our formula is going to be slightly different, but it matches up with what we've been doing. So this is a 2-sample t-test for difference of means. We're going to do a mu1 minus mu2. We want to state that order in our thing. Make sure we state the order. Especially when we get to our conclusion. Do we have independent random samples or random assignment of treatments? We got that. Approximately normal condition. And sampling without replacement. We want to check the 10% rule. So we're good there. Name. Conditions. Our parameters and our hypotheses. Again, very similar. We're just comparing two things. Now, this is worth noting. We're going to assume that there's no difference. So mu1 minus mu2 should equal 0. That's assuming no difference. That is an assumption. Usually it's going to be the case. Very rarely would it be anything else. Which means in our formula, when we're taking our sample statistic, we want to find the difference of those and subtract the parameter difference, which should be 0. So it's almost always going to be 0 there. What changes in the bottom? It's 2 samples, so it's not just s over the square root of n. We're going to combine them. The square root of s squared over n1 plus the square root of, s2 squared over n2. All right? Worth noting, we still need to use our degrees of freedom. It's still going to be n minus 1 for the smaller. We are always using the smaller, more conservative one. Make sure you're doing that just like with confidence intervals. And just a couple notes. There's going to be a way I can show you with technology to do that. But otherwise, use the smaller one. And we're stating difference of means in our conclusion. So formula, notes. So back to that problem then. If I want to find a t-value, I'm going to use this formula that just magically showed up. But I'm going to plug in all the values that I have, right? So in this case, t is going to be equal to, we were given the x bar. I'm going to do 14 minus 1975. So 41.91 minus 38.97. The order doesn't matter as long as you're consistent throughout. I'm going to do that order just so that I have positive value here. Subtract the difference in the means we're assuming that there's no difference. So that's going to be almost always 0. Square root of our standard deviations were 14.35 and 13.13. And that was out of 1501. So 13.13 squared out of that 764. Common thing that I see people missing is squaring that s part on top. Do all your math. Use your calculator if you need to. I got a 4.881 t-value. Now go to TCDF. I'm going to use the degrees of freedom. The smaller of the two would be, well, 763, technically. Will give me a p-value equal to 0.0000000. Well, I have to double it, so it's 0.00714. But I have to double it because it is a two-sided. I still get essentially 0. So I'm going to do 0.0000 plus, because then there's still a couple more zeros. That's going to be my p-value. And that's what I'm going to use to make my conclusion. Either way, it's really small. So because it's so small, I can say we're going to reject the mean. Sorry, the null. It's less than 0.05. That's what it said to test at. We reject the null. There is convincing evidence that the number of hours worked in 1975 and 2014 are different in America. Or some wording of that. They are different. We found evidence that there is a difference. And that's how we can go about doing one of these two-sample t-tests. So what I'm going to do is I'm going to leave you with this. I'm going to have you try this one. Read through the two things. And this time we're given individual data. Oops. There you go. And you have to, again, do a two-sample t-test. Ultimately, we're looking at comparing calcium and a placebo group for this randomized experiment to see, well, is there convincing evidence that the calcium supplement reduces blood pressure more than the placebo? That's what we're looking for. We want to know if calcium supplement reduces blood pressure. So why don't you pause and try that one? All right, some things I want to note for this. Hopefully you got at least this one worked through and tried. You have the data. You have to use one variable stats, whatever you want to do to find your mean and standard deviation to see the difference in the blood pressure levels. And what's the change? So group 1, if you found the average, that's the calcium group, you should have gotten 5.0 with a standard deviation of 8.743. For our second group, the average was negative 0.273 and a standard deviation of 5.901. Okay. Now, when we're getting into this, parameters would be the true mean reduction in blood pressure for taking the supplement, and mu2 would be the true mean reduction in blood pressure for patients like these that are taking a placebo. So like a reduction, if it's saying X bar was 5, that means it went down 5. If it was a negative, that means it actually on average went up. So our hypotheses are that these two things are equal, that there is no difference. Again, another way to write this would be that mu1 minus mu2 equals 0. So some people do write them like that. You could do mu2 minus mu1 equals 0. It's just showing that there's no difference. We're saying that we think that there is a greater increase by this one than this one. So we think there's a decrease in blood pressure using the calcium supplement. Okay, so we're going to test that. Conditions, random assignment of subjects to treatment groups. So yes, that was stated. So hopefully you checked that one. Normal distribution of blood pressure reduction. So we have to go back up to those values and make ourselves like a rough sketch. We don't have enough value to use the central limit theorem. So I'm just going to go like in this range to 0 to 5 to 10 to 15. And I've got 1, 2, 3, 4. I had 1 here, and 2 in each of these. Not perfectly normal at all, but not like a crazy skew. There maybe is a slight skew. This is probably iffy, but this would be for the calcium group. Now for the placebo group, I did a similar thing, but it actually was lower. So we had all the way down to there. And we had none in the second group, but so there's a little bit of a potential outlier there. So I would note both are iffy, or something along those lines. But we're going to say okay to proceed. So I wouldn't say there's a huge skew or clear outliers, but there is definitely some skew to both of them. So we're going to go on with that. We don't have to check condition 3 because it's an experiment. Nice. So just 1 and 2 for this one. Now getting into our formula, to find our t-value, we have to use those values that we found, which were up here. And we want to find the difference here. So we're going to do mu1 minus mu2. It's going to be 5.0 minus negative 0.273. Okay? From there, we're going to subtract 0 because we're assuming there is no difference. And all this on the bottom. So 8.743 squared over, we had 10. This is 5.901 squared, and this was out of 11. Sorry, we had different numbers for each of those two groups, but they were close as we could get them, which does give us a t-value of 1.604, which is reasonable. With the degrees of freedom of the lower of the two, we're going to use 9. 10 minus 1 is 9. Get a p-value of 0.0716. Now, we're testing at, it does not say what level we want to test at, does it? Now, if it doesn't say that, we're going to use 0.05, but you could potentially have said, if you use 0.1, it's a little different. So we're going to say we're going to use 0.05 because that's the most common alpha value, but because 0.0716 is greater than that, we fail to reject. We do not have convincing evidence that the true mean reduction in blood pressure is higher for subjects like these who take calcium than for subjects who take the placebo. It seems like it was clear, like it would have been higher, but because we don't have enough data, there's not quite enough to say that it is for sure. So this small sample sizes make it harder to reject. Okay. So the only follow-up question I have for that is to make sure you can interpret the p-value. We got that p-value of 0.0716. So as a refresher, we are assuming that there is no difference in the true mean reduction in blood pressure for subjects taking calcium supplement and the placebo. So we're assuming that there's no difference. If that's the assumption, there was a 0.0 or a 7.16% chance of getting a difference in sample means of, well, in this case, 5.273 or more. Because the difference in sample means was x bar 1 minus x bar 2. So that would have been that 5.0 minus that negative 0.273. If you subtract those, you get 5.273. So that would be the difference. That's the difference between the two from our samples. Just by chance of a random assignments, of all random assignments of 21 subjects. It's a little bit different just because of the situation, but very similar to what we've been doing. All right? And that's the idea of two-sample t-tests. Could be with samples, could be with experiments. But the process is so similar, we just have to look at those mean difference, or the difference in those means is what we're looking at. All right? And that's section 10 or 11.2b. We'll see you next time.